So, hello and welcome to the 45th session in the AI Safety Reading Group. Today we'll talk about an article called Building Safe AI by Andrew Liam Trask. Andrew Liam Trask is a PhD student at Oxford University specializing in deep learning, and he has a blog, I am Trask, at GitHub, where he has this quite recent article about a tutorial for encrypted deep learning. Now, a tutorial is quite different from the kind of articles we normally read, because it's not really attempting to introduce in a theoretical way subjects, but showing hands-on how do you actually do this. And this is one of the exciting things about deep learning, that it's actually not that hard to get started with. So it's possible to have a short and meaningful tutorial on this. I will not go through the programming code in this. I will focus on the things that have some kind of application to AGI safety, to superintelligences and this kind of thing. There are also other uses for encrypted deep learning, such as data privacy, and I will not cover those here. So why do we want to encrypt deep learning? The goal here is to make an cryptographic AI box. The classic way to control a superintelligence is to put it inside a box and only let it answer questions or have very limited impact on the world. Of course, the problem, at first thought, you think that having an air-gapped AI box would be impossible to break, but actually there have been many books written about how to get across these air gaps. There are many so-called side channel attacks and ways to get around building an AI box. It's actually really difficult to do. And this is not the only problem with AI boxing. The other problem is that the output channel, the thing that the superintelligence tells you, it might be able to manipulate you very strongly. So this is considered the main vulnerability of AI boxes, and that's not what we are focusing on here. So the idea of making a cryptographic AI box was invented by Paul Cristiano in 2010, and the first place he wrote about this was in this page on Less Wrong, on this post. And the idea is present on Alexei Turchin's map, the one we read last time. If I just move here, in the part on AGI safety map, where on external constraints we have AGI confinement, the box, as one of the, here has written that it's a marginal solution. And at the very bottom you can see a crypto box, Homomorphic Encryption by Cristiano. And this is exactly what we are looking at today. So why would you want to build an AI into a box? What is the goal of doing that? The general AI boxing strategy is that you build an AGI that's capable of self-improving, that is, and then you don't turn it on until it's inside some kind of box, and then you ask this possibly unfriendly, possibly unaligned, possibly friendly. You try, of course, to make it friendly, and ask it to provide not just the source code for a friendly AGI, but supply a proof that it is friendly. And of course, this proof, it would be wonderful if there is an easy way, if we can automate this, so there's an automatic program that verifies if an AGI is friendly. Then this approach would be really neat. And also in many mathematical and computer science contexts, it turns out that verifying a proof is a lot easier than finding a proof. So it is indeed possible that there is a superintelligence capable of giving a proof that a particular AGI is friendly, and unable to fake this proof. There's a huge difference, and that's kind of the hope. This is kind of a marginal solution, because it might be that AI boxing is impossible because a super intelligence either would not be smart enough to build a friendly AGI, or too smart so it can cheat us in any cases. But it is possible, it is plausible, or at least thinkable, that an AI box will solve the control problem. Deep learning and homomorphic encryption. Deep learning is a somewhat new kind of artificial neural network. An artificial neural network is a computational model that is very much inspired by the brain, uses some small components that are modeled as neurons. It's not directly modeled on the brain. Inspired would be a better word. And the deep part in it is that it doesn't just have input and output, but some layers in between that allows things that are kind of like transformations and feature extractions I've written. It's actually very unclear exactly what happens in the deeper layers of deep learning. Fortunately for our purposes here, the deep aspect is kind of irrelevant. The only reason why everybody's talking about deep learning is that in practice of all the AI techniques we have, then deep learning outperforms every other technique by a rather large margin. So that's why everybody's talking about the deep learning, because in practice it works really, really well. Homomorphic encryption. Now, standard encryption takes a plain text and turns it into a ciphertext, scrambles it, encrypts it in a way so that you need a secret key to reveal what was the encrypted message. And homomorphic encryption is homomorphic means the same form in Greek, and this means that the result you get from the encryption in some way have the same form as what you had decrypted. And I've taken some of the code here from the tutorial to try to illustrate what's going on. So here we have an array, a list of integers 0, 1, 2, 5. And we start by encrypting this array here, and then we get something called C, that is the encrypted. If we try to decrypt it, of course we get the same array back. We get 0, 1, 2, 5 back if we decrypt what we've just encrypted. The funny thing about the homomorphic encryption is if we work on the encrypted data, for instance, add it to itself. Normally, if you take two encrypted things, you would get something completely random. But here, for homomorphic encryption, you actually get a very meaningful result. You get the same as if you're taking the unencrypted and added it to itself. So 0 plus 0 is 1, and 5 plus 5 is 10. You can also multiply with this. You can say we'll have every value 10 times larger while it is encrypted, and then you will get the meaningful results out. And this is something that only happens for homomorphic encryption. And this is also something that requires a lot of work to get into, to actually make a homomorphic encryption algorithm. So if we want to encrypt all the values of a neural network homomorphically, then we need an encryption algorithm, it's actually quite recent. In 2009, the first real homomorphic encryption algorithm was discovered. So I remember that the box was the homomorphic encryption box idea is from 2010. The first algorithm was from 2010, and it supports addition and multiplication. And addition and multiplication is not enough to build a neural network if you can only do these things. You need to have some more operations to be able to do that. And of course, if you know how to add things and you know how to multiply things, then you can multiply them by -1, and then you have subtraction, and 1 divided by multiplication, you multiply with the inverse factor, and then just because you have addition and multiplication, you'll also get subtraction and division, and exponentiation if you want a number to the third or something, then it's just multiplied several times. That also works out quite well. You will need some other mathematical functions in order to make a neural network. You will need inverse tangents and the sigmoid logistic functions. Fortunately, the homomorphic encryption, even if it doesn't support this, it doesn't matter very much, because they can be approximated using something called Taylor series. I won't go into that, but you can use these up here, addition, multiplication, and exponentiation, to actually approximate almost all functions. So just, even though it looks, if we go back to the slide here, like you could only add things and you could and multiply them, and that looks really limited. It turns out that if you are capable of doing addition and multiplication, you can do some very advanced stuff, and it's not really difficult to do. And part of this is because the approximation, the reason why it works very well is that there's actually in the homomorphic encryption elements, the way they work is also by introducing some noise, and then you do some rounding, and then the noise is cancelled out. That's the way the homomorphic encryption works. I won't go into many details about this. Just say it takes a long time. A long time, really. It used to, when it was first discovered, it took 30 minutes for a computer to make a single addition. So that's way slower, of course, than the computers that were used during the Second World War. But newer algorithms are down to one operation in 2 seconds, and so I calculated that is a half time of less than 1 year, meaning that more than once every year these algorithms appear to get twice as fast. So it's improving very quickly. What speed would be useful? That's a very interesting point, because we would expect many of the deep learning algorithms that are used now are extremely CPU intensive, meaning that this encryption would give a completely unacceptable performance penalty during training. When you actually use it for something, then this lower speed matters very little. The problem in creating deep learning is it takes a long time to train the networks, but actually running them takes very little time. I would expect, of course, these numbers are way too high to be useful for any meaningful things. But the big problem is, the big open question is, when we get a general AI, will it be something that comes as a result of a software breakthrough, or as a result of throwing a lot of extra hardware on rather simple algorithms? If it requires a lot of extra hardware and huge number of operations, then this will be a slowdown that is completely unacceptable. If it turns out that there's a theoretical breakthrough, someone figures out how to make neural networks much smarter without requiring too many more computations, then homomorphic encryption might be very feasible, even if it is a lot slower. But for this case, of course, we're here at a tutorial. Trask goes through a number of algorithms that some are very fast, some are more secure, some support fewer or less operations. And in this case, in the tutorial, they choose an algorithm that is very fast, or not super slow, I should say, and not super safe either. So it might not be extremely secure, but for a tutorial, I think that's a good choice. So that's an implementation. And if you go to the article, there's some explicit Python code that you just put into you can put it into Notepad++ or some whatever IDE you use for Python, and then actually just run it. And it's I haven't done it myself, but I've heard from others that it's actually quite possible to start with, at least with simple neural networks. Here, Trask has another article called A Neural Network in 11 Lines of Code. And even though these 11 lines of code are kind of difficult, they are not completely impenetrable. I don't know much Python, and I can read it and understand what's actually going on. And the other examples, the homomorphic encryption algorithm is also implemented in Python here, and they show the neural network, and they show how to combine it, and they show also some pre-computations that happens for performance reasons to try to speed this up, which is somewhat necessary, because 2 seconds per operations is kind of slow, no matter how you look at it. There's also one thing you have to do whenever you have neural networks, something called tuning. And Trask writes that it is kind of clunky to do it with this encryption. He tries different ways. Here you can see here how he ends up doing it with something like I should say first, the real problem that he's looking at is IMDb, Internet Movie Database reviews, looking at the words people use and figure out which words are positive and which words are negative. And here he says he disregards all words less than 10, and they have to be a reasonably strong signal, and 8 hidden notes. That's the deep part of the deep learning. In this case, that there are a layer in the middle with 8 nodes and a learning rate. These are things that you kind of need to almost on an ad hoc basis, when you set up a neural network, figure out how to tune it exactly. And then he shows this works, and he doesn't show how good the classification is in the beginning. He shows 2 data points. After 100 examples, it can predict whether a review will be positive or negative with 65% probability, and 1,000 examples that puts it up to 75%. So he shows that this is actually working. So in this way, the tutorial on building safe AI, it's quite possible. It's quite approachable if you're interested in deep learning, and it definitely shows as a proof of concept that Paul Christiana's homomorphic encryption algorithm idea are viable, but whether it is a complete solution to the control problem, that is, we are probably reasonably far from that. So, thank you for watching, and now we'll discuss the article, and I'll stop the video.